Now we get some practice going from radical form into rational exponents. Because that a inside the radical is an a to the first power, this is going to become a to the 1/4. This next problem will become z to the 5/6. And for problem 10, we would have a to the 2/8, b to the 4/8, c to the 7/8. But we can always reduce fractions, so we would write this as a to the 1/4, b to the 1/2, c to the 7/8, like that. Rational exponents give us a lot of power that we don't have when we're using radicals. Let me just remind you that all the properties that you know for exponents apply here, at least exponents with real numbers. You can add exponents. So in this case, we could have 2 to the 2/3 minus 5/3, which would equal 2 to the negative 3/3. You know that to equal 2 to the negative 1st, which is then equal to 1/2. When you are dividing with a common base, you can subtract exponents. So in this next problem, we have q to the 5/4 minus 1/4, which is q to the 4/4, which basically can be written as q to the first or q. When you have this product all raised to a power, you can shower that exponent inside and multiply exponents in each case. So we would have x to the 4th times x to the 3rd, and you know that that's going to become x to the 7th. For number 14, rather than work inside the parentheses first, I'm going to apply this negative x4 exponent to both the numerator and denominator, multiplying exponents as I go. The numerator becomes m to the 1st because 1/4 times 4 is 1, and the denominator becomes n to the 2nd, and that basically is our simplified answer. Now we could have done extra steps. We could have worked inside the parentheses first and then apply the power, but that one came through a lot quicker just working with it directly. For this final problem, since I don't have a negative exponent outside these parentheses, I'm going to apply the property of negative exponents inside the parentheses to move these a's down to the denominator. So this first parentheses becomes b to the 1/2 over a to the 1/3, all to the 4th power. And the second one becomes b to the 3/5 over a to the 1/2, all to the 10th. Then I'm going to apply the outer exponent to the entire parentheses, raising both the numerator and the denominator, multiplying exponents as I go. So this is going to give me b squared over a to the 4/3 times b to the 6th over a to the 5th. Now what we've got to do is we've got to multiply across. You know we're going to have b to the 8th in the numerator by adding exponents, and we're going to have to deal with fractions here. We're going to have 4/3 plus 5 over 1, and I'm going to write that 5 as a 15/3, and that will give me a to the 19/3. Now, that is probably the way that the book would ask us to write the solution, because it said do not use negative exponents in your final solution. However, note that this is not simplified. We really don't want that. What I would do to simplify this is I would need the denominator not to have a fractional exponent. If I were to multiply by a to the 2/3 over a to the 2/3, notice how the denominator would now have a to the 21/3, which would be a to the 7th. And then the numerator would be a to the 2/3, b to the 8th, and I'd have a rationalized denominator. Now, how did I choose a to the 2/3? Well, I knew that this was a 6 1/3, and I'd have to get rid of that fraction, and it needed 2/3 more to get up to a whole number of 7, and so that's what I chose to multiply by. But in this problem, odds are your teacher would be accepting this answer, or that would be what's in the back of your book or online, because of how the directions are worded. Technically, however, because there's no fractional exponent in the denominator, this final form is considered to be simplified.